So good morning, everyone. Welcome to this 9th lecture of memory design and test course. And today we will try to, see if we can cover the memory periphery circuits towards its completion. Otherwise, we will just first close the memory I/O circuits and then start with the decoding logic. Okay. So before we start, what were you doing in the last class? Any questions from the last class also, please?
Yes, sir. Questions, sir.
पहले क्या कर रहे थे फिर questions में?
So we look different input output components in memory architecture, but at the bitline pre-charge, column marks, output buffer. So first we look into we check if we place the sense amplifier above the mugs or below the mugs, what were the impacts of placing the sense amplifier above and below the mugs. Then we look into the bitline pre-charge.
Okay. Let me re-synthesize. Okay. So what we started to look at was what are the various circuits which form a part of a memory I/O. That was where we started from.
Yes, sir.
And we saw that there are pre-charge blocks, there are column multiplexers, there are sense amplifiers, there are write drivers, output buffers, input buffers, and so on. Yes, so many different kinds of circuits exist in a memory I/O. Okay. Then we entered into the discussion of where should the multiplexer be placed. Should it be above the sense amplifier or below the sense amplifier? So what happens if we put the multiplexer below the sense amplifier?
So then there are many sense amplifiers which will cost a huge area.
Okay, so there is a huge area penalty. Is it only area or something else also?
It is area.
Speed area.
Speed increases, but we have a huge area penalty.
So you were talking about leakage also. Maybe the leakage was more in that case. If
what about dynamic power? What would happen to the dynamic power?
It would increase.
So power will also increase.
So power will increase, area would increase, leakage would increase. Speed can be better, a little better.
Sir, I mean, why would the dynamic power increase? Shouldn't it decrease, sir? Because like if we are suppose placing the sense amplifier below the say below mux, then and if I am placing above the mux, so you're talking about the below mux right now, or the above mux.
Above the mux, what happens?
So then the dynamic power should not increase, na? It should be less as compared to when it's below.
Why?
So like because for example, sir, like if we are placing say below the mux, then you talked na ki we have the additional RC coming into picture. So that will also need discharging, kind of charging or discharging. So that is basically additional dynamic power, na? But if you are placing above the mux, that is not basically there. So dynamic power should decrease, na?
So how many sense amplifiers are there when we have it above the mux? Let us say it's mux 4. So how many sense amplifiers will be there?
So the number of the bits, how many bits are there? That many muxes.
Is it
that
number
many
of
sense amplifiers
per I/O? How many sense amplifiers will be there per I/O? If the sense amplifier is above the mux, how many sense amplifiers will be there per I/O?
So I mean the number of how many bits are there per number every word, that depends na ki how many sense amplifiers.
That is when the sense amplifier is below the mux. If the sense amplifier is above the mux, what does this mean? That the output of the sense amplifier has to be multiplexed.
Yes, sir.
So how many sense amplifiers will need to be there?
So it depends upon the number of inputs of the mux.
So if it's a 4:1 mux, then 4 sense amplifiers.
Yes, sir. 4 sense.
So if you have more sense amplifiers that are operating, will it be more power or less power?
Yes, sir.
So area increases, dynamic power increases, leakage increases, performance improves. Now to reduce the dynamic power, you may say, okay, even though there are 4 sense amplifiers, I already know what the mux address is. I will not activate the remaining sense amplifiers. Okay, you could do that, but then you're putting extra load on mux. So mux capacitance, mux signals will be routed extra. There will be some extra capacitance that needs to be handled there. But yeah, that could be done. but that would also not mean that dynamic power is lesser than when the sense amplifier is below the mux. You cannot straightforward say. It would depend a lot on the layout and the parasitic capacitances that will come into picture. Are you able to see this?
Yes, sir.
There was a question on this only in quiz, sir, actually. So putting right driver below mux improves speed. That was the like statement that has been given. And the question is that which of the following is not true? So, sir, if we look into the perspective, I'm like, if you look into right driver, we'll be looking it from the, if you look into it with respect to the data perspective. So if I put my right driver below mux, उसका मतलब ये होता है कि I'm putting my right driver in between my peripheral and my mux, right?
Input and mux के बीच में there is this right driver, and then there is the bit line. After the mux there is a bit line.
After, yeah. So it's in between the peripheral and the mux, right? So I think that option should be मतलब wrong. That option should be wrong, I think, because
That
putting
is
right
something you
driver.
will get to see in the results. What do you think it would be?
I
क्विज के अंदर क्या आंसर है वो तो आपको क्विज के रिजल्ट में मिल ही जाएगा ना. Now let us discuss what should it be. Will having one right driver improve speed, or should I put right driver above the mux so that I can improve speed?
सर वही मेरा डाउट है सर, मतलब ओके अबव द
लॉजिक लगाओ.
नहीं सर, अब मेरा डाउट ये है कि अबव द मक्स का मतलब क्या होता है एग्जैक्टली, पेरिफेरल और मक्स के बीच में या फिर मक्स और ये इनपुट के बीच में?
What was it when we looked at the layout, when we looked at it in the class? What did it mean?
सर अबव का मतलब ऐसा होना चाहिए कि एरे और हमारे मक्स के बीच में भी
है ना?
Yes.
Above means between array and between bit line and mux, and below mux means it is between mux and IO.
Okay, sir. Okay.
So what would happen to the speed now? Tell me.
Sir, if it's in between mux and IO, then the speed will decrease. If it's in between and like mux and the bit line, then the speed will decrease.
Then the speed would improve. Okay.
Yeah.
Great. So how many types of multiplexers did we look at?
Two types, sir.
Which were they?
One is the tree type. The other, I don't remember the name, sir.
Column decoder, there was no name for that.
There was no name. It was a transmission gate based. Huh? So what is the disadvantage of a tree type decoder and what is its advantage?
Capacitance is very high in tree type, sir. I mean,
सर ट्री टाइप में स्टैक था सर हमारा इनमोस्ट का, तो वहाँ पे हमारा बेसिकली बहुत ज़्यादा ओवरड्राइव कम हो जाएगा, तो हम अल्टीमेटली ड्राइव नहीं कर पाएंगे.
So in a T-type decoder, there was lots of NMOSs that were coming in the series. So you would lose signals and you would need to have much stronger drives, and or you will not be able to operate at low voltage at all.
सर एक्चुअली मेरा वो प्रीवियस वाली जो हम कर रहे थे डिस्कस में डाउट था कि सर जब हमारा सेंस एम्पलीफायर अगर हमारा अबव द मक्स है, तो एटलीस्ट जब मैं एक वर्ड को रीड करूंगा तो आई विल बी रीडिंग ऑल द बिट्स ऑफ दैट. सो अल्टीमेटली अगर मेरे मान के चलिए मेरे 8 बिट्स हैं, तो मुझे 8 एम्पलीफायर में चाहे मैं मक्स के बाद हो चाहे मक्स के पहले हो, वो तो मुझे करनी है ना डिस्चार्ज, मतलब वहां से
8 तो करना ही है.
यस सर. सो बट अगर आप ऐसा बोल रहे हैं कि अगर मेरा सेंस मक्स के ऊपर है सेंस एम्पलीफायर, तो मैं हर मान लीजिए मेरा मक्स 4 है, तो मैं 30 मतलब कि आपने सॉर्ट ऑफ की 8 तो वर्ड 0 के करूंगा ही करूंगा, बट बाकी वर्ड 1 वर्ड 2 वर्ड 3 के भी 8 कर रहा हूँ, मतलब उसकी वजह से डायनेमिक पावर इंक्रीज हो रही है.
हाँ, मतलब उतने सारे सेंस एम्पलीफायर्स लगाने पड़ेंगे ना राघव.
सर बट वो तो ऑफ होंगे ना सर, मतलब
ऑफ कैसे होंगे? मक्स को यूज करोगे इसका मतलब सेंस एम्पलीफायर एनेबल के अंदर मक्स की इंफॉर्मेशन को ऐड करोगे.
अच्छा ओके.
ऐसा करोगे, कर सकते हो, मैंने बताया तो ऐसा कर सकते हैं, बट दैट इज नॉट द डिफॉल्ट मोड ना. उसमें एक्स्ट्रा सिग्नल्स जाएंगे, एक्स्ट्रा पावर उसकी उन सिग्नल्स को जनरेट करने के लिए भी जाएगी, सब कुछ होगा. कंट्रोल मशीन थोड़ी सी कॉम्प्लेक्स बनेगी, लेकिन कर सकते हैं, करते हैं, क्योंकि अदरवाइज तो बहुत ज्यादा डायनामिक पावर बढ़ रही है. बट अगर मैं सीधा कहूँ कि एक ही एसएन सिग्नल था, अब उसी एक एसएन सिग्नल को कैसे ऊपर लेके जाऊं, तो फिर सारे सेंस एम्पलीफायर एक साथ एक्टिवेट हो गए ना, है ना?
ओके. मेरे 32 के 32 हो जाएंगे एक तरीके से सॉर्ट ऑफ.
या
ओके. सर और एक और चीज थी सर, जो राइट ड्राइवर एंड सेंस एम्पलीफायर है उनकी जो प्लेसमेंट है अबव एंड बिलो द मक्स, वो हम इंडिपेंडेंट देखते हैं या फिर वो लाइक रिलेटेड है कि मतलब अगर मैं सेंस एम्पलीफायर को ऊपर रखूंगा तो राइट ड्राइवर मेरे ऊपर होगा, या फिर मेरा सेंस एम्पलीफायर नीचे है मक्स के तो राइट ड्राइवर भी नीचे होगा, या फिर दोनों इंडिपेंडेंट हो सकते हैं कि एक ऊपर एक नीचे है?
You tell me.
सर एक्चुअली में डाउट आ रहा था क्योंकि एवरी बिट लाइन जो
What
है,
do you think? See, doubt आ रहा था, but what is it that you are leaning towards?
सर एक्चुअली मैं ऐसे थिंक कर रहा था कि इफ देयर इज अ bitline pair, so every bitline pair will have its own set of if we don't think of mux, every bitline pair will have its own will have its own sense amplifier and its own right driver. So दो kind of circuitry हैं. तो अगर आप सेंस राइट ड्राइवर जो है उसका तो पता नहीं, बट राइट ड्राइवर परफॉर्मेंस का इशू आता है और दोनों सेम ही चीजें हैं, अगर ऊपर रखता है तो दोनों परफॉर्मेंस बढ़ता है बट एरिया बढ़ता है आपका, और लीकेज बढ़ता है, पावर बढ़ता है. दोनों में नीचे रखना तो आपका एरिया इंप्रूव होता है, बट आपका सेंस एम्पलीफायर में डिफरेंशियल जो है थोड़ा कम होता है, तो आप कम डिफरेंशियल में भी कर सकते हो, बट राइट ड्राइवर में आपको पूरा डिस्चार्ज करना
जो
होता है.
तुम्हारा सवाल था उसका जवाब क्या है?
सर वही
ये सब
समझ
तो
नहीं आ
हमने
रहा कि
establish कर लिया. Whatever you just now said, we just established in the class just now, is it
यस
not?
सर, यस
So
सर.
what is the answer to your question? What according to you is the right answer? It may be wrong, don't worry. Just what according to you is the right answer.
Sir, according to me, if I will see ki which operation is more critical, write or read, and then basically maybe that may decide ki if write is, I'm thinking ki मेरा bit lines जो हैं पूरा discharge
The question was, is it necessary to keep both right driver and sense amplifier up above the mux or both below, or can I keep them independently? That was what
yes
your
sir,
question was.
yes
What is
sir.
the answer? Can you do it or not you do it? Can you not do it?
So on the face of it, it looks we can do it.
Yeah, we can do it.
Acha, okay.
Okay, when we do it, let us say I put the, now this is a question to everyone again. If I put the right driver above the mux, how would it change my mux? Let us say we use the transmission gate mux earlier. So if I put the right driver above the mux and sense amplifier is below the mux, how would the mux change? How would the transmission gate mux change?
Sir, transmission gate mux किसकी बात कर रहे हैं सर, ये समझ नहीं आ रहा.
We just saw, no? There are two types of mux. One is tree type and another is simple transmission gate mux, where the
Okay.
decoding is done separately and you get the decoded address.
Yes, yes.
Yeah. As a designer, think.
तो जो ओरिजिनल था बेसिकली जिसमें हम PMOS यूज कर रहे थे.
Yeah.
Okay, okay.
So as a designer, how will it change? Anyone? Hello? The 30 of us. कुछ भी जवाब दो यार. गलत होगा ना, क्या फर्क पड़ता है?
Sir, right driver, if you put it above the column decoder marks, so if I want to discharge my bit line, so there should be a closed loop, right? And like ये marks बीच में होगा तो I am supposed to have this signals on for the column decoder. As my actually I mean I don't know, I am unable to interlink that. I'm like keeping the right driver above this column decoder. मतलब imagine करने के लिए थोड़ा मुश्किल हो रहा है सर.
Yeah, I know. See, it is not obvious to you. That is why I'm asking you.
Sir,
See,
अगर मेरा
the course is not just about me telling you things. The course is about me making you think also. Is it not? Unless you think like a designer, how will you become one? Unless you think like a designer, how will you connect the dots that I have given you? So I'm insisting, connect the dots. Ranjit,
सर
you're saying
राइट
something.
ड्राइवर का मतलब जस्ट मतलब एक पीमोस या फिर एनमोस होता है जिससे हम लोग मतलब डिस्चार्ज करते हैं, राइट? मतलब
Welcome to the right driver just now. My question is about the mux. How would the mux evolve?
सर जो हमारी बिट लाइन और बिट जीरो थी सर, वो हमारी राइट ड्राइवर से कनेक्ट होंगी और फिर बेसिकली हमारा मक्स कनेक्ट होगा. तो सर हमारे केस में डेटा बार मुझे बाहर चाहिए, तो बट सर चेंज तो कुछ नहीं होना चाहिए, मतलब सर चेंज क्या होगा सर? ऐसे ही
Okay,
रहेगा.
let us see. Yes, Deepank?
So maybe mux should also have a demux kind of operation. It should work two way because one way is
Also,
required
anyway,
for.
it will always do that.
Okay. So
Sir,
While we are calling it a mux, it is a two-way process anyways. है ना? So that is not a challenge. Ranjit?
sir, basically there should be no change in the column decoder as such.
Okay.
सर एक चीज हो सकता है अगर राइट ड्राइवर और सेंस एम्पलीफायर को नीचे रखते हैं मल्टीप्लेक्सर से, तो मे बी द चांस कि मुझे लग रहा है ऐसा कि जब राइट ड्राइवर चार्ज करने जाएगा बिट लाइन को, तो बिट लाइन का कैपेसिटेंस आएगा, और चूंकि मल्टीप्लेक्सर का आउटपुट जो है कनेक्टेड है सेंस एम्पलीफायर से और राइट ड्राइवर से, तो सेंस एम्पलीफायर का भी कुछ इनपुट लोड कैपेसिटेंस होगा, तो यहाँ पे एक्स्ट्रा उसको चार्जिंग करना पड़ेगा आई थिंक।
सर एक और इशू दिख रहा है मुझे सर, अब शायद से सर अगर मैं राइट ड्राइवर को ऊपर रखता, अगर मैं नीचे रखता हूँ मक्स के, तो सर बेसिकली मेरा ट्रांसमिशन गेट जो था, ओके वो तो मेरा पीमॉस बेस था, तो वो जीरो तो ले नहीं जा पाएगा वहाँ पे।
ट्रांसमिशन गेट PMOS बेस कैसे होता है?
अच्छा ट्रांसमिशन गेट है, सॉरी सर, यस सर बट अच्छा ओके हाँ सॉरी सर।
Anyone else? Don't even want to try? अभी तो मैंने बताया भी नहीं कौन सही है कौन गलत है. You may just say yes, I think Raghav is right, or that is also fine. Speak up. Okay. Now tell me one thing. Why do we need a transmission gate in the column multiplexer? What if I had used only the NMOS or the PMOS only?
Sir, perfect zero, perfect one.
Full zero or full one.
Zero and full one.
I will not be able to transfer a full zero if I have a PMOS only mux, and I will not be able to transfer the bit line discharge for the sense amplifier if I have a NMOS only mux. That is how we put a transmission gate. Now, if I put the right driver above the mux, it is directly on the bit line. Do I need to transfer a full zero at all? Is this
Not using
helping
mux,
now?
not using mux sir.
The mux does not need to have the NMOS then.
Hmm.
Similarly, if my sense amplifier is above the mux, do I need to transfer VDD? Do I need to transfer VDD?
सर जब सेंस एम्पलीफायर ऊपर रखोगे मक्स के, तो आप सेंस एम्पलीफायर लैच दोनों को ऊपर रखने की बात कर रहे हो एक साथ, ऐसे बोल रहे हैं सर? मतलब
सेंस एम्पलीफायर ऊपर है तो उसकी मतलब उसका आउटपुट भी लैच कहीं तो हो जाएगा ऊपर ही, या मक्स के बाद भी हो जाएगा तो क्या फर्क पड़ता है. बट डू आई नीड टू ट्रांसफर एनालॉग VDD? That is my question. Below the mux, from the bit line to below the mux, do I need to transfer something like that?
Sir, these are connected in series, right? If they are connected in series, then I mean,
ट्रांसमिशन गेट सीरीज में होता है.
ट्रांसमिशन गेट नहीं, मतलब जो भी सेंस एम्पलीफायर और ट्रांसमिशन गेट जो दोनों जो भी है, so they'll be connected in series, right? So you were speaking about, for suppose PMOS gate
The
only.
transmission gate is used to connect the bit line and the sense amplifier. Now, if you call it series, you call it series. That is your nomenclature. I never use the word series there anywhere. You call it whatever you want to call it. I have no problems. But I never use the word series. So I don't know what to
Sense
say.
amplifier in between the transmission gate and the data output which we take. That's what you were saying. Or above the transmission gate.
I'm saying bit line, transmission gate, and sense amplifier.
second.
So do we need
do
we need a transmission gate there, or can I do with only the PMOS?
We need a transmission gate over there, obviously, because sir, I mean, we need a perfect zero and perfect one, right? So
Where?
I mean,
Where do you need? At the sense
data
amplifier.
position.
At the sense amplifier, you need a perfect zero and a perfect one as an input.
No, sir. I think that is why we were using sense amplifier to sense the like minimum value. So why do we need the full zero or full VDD?
So do I need a full transmission gate there?
No, sir.
No.
Hmm?
But after the sense amplifier, the pit line outputs will be transmitted to the mux, no sir. So at the mux, we need the transmission gate. No,
That will be a digital mux anyways. वो तो आप NAND gate से implement कर लोगे. My question is, the bit line is otherwise connected to a transmission gate through which you transfer all levels of bit line that toss down to the, you multiplex any level, analog level of the bit line. That is the purpose of a transmission gate mux, is it not?
Yes, sir.
Once you convert it into digital, then the mux can be simply digital mux.
Yes.
It will be AND gate mix करके आप बना लोगे. That is logic. So as a designer, I'm not worried about that as much. But I'm just seeing, can I reduce area somewhere? Can I do something? That is where my question is coming from. So do you think on the bit line, I can reduce its load and keep only one mux, one transistor, not two?
सर आई मीन अगर आपने सेंस एम्पलीफायर ऊपर रखा है तो आपने लैच जब किया तो आपने फुल बेसिकली स्विंग आ गया, बस वीडीडी और दोनों आ गए हैं, तो फिर आपको एनालॉग ट्रांसमिशन की जरूरत नहीं है वहां पे मक्स में फिर.
तो फिर पीमॉस रखना है या नहीं रखना है?
सर आप मतलब एक तो रखोगे, मतलब पीमॉस या एनमॉस?
Sir,
मेरा
it
सवाल वही है.
becomes
What do you
real
want to keep? Sorry?
right in right cycle we want an NMOS. In a read cycle we want a, in right cycle we want an NMOS and read cycle we want a PMOS over there. Right? मतलब sense amplifier use कर रहे हैं तो उसके लिए I think I need an NMOS over there because sense amplifier से I can get a full VDD. And वो तो dual case हो गया ना सर, मतलब वैसे भी area बढ़ रहा है वहाँ पर.
So what did we say? We want to say that there is a sense amplifier up there. Then we put a mux. And then there is this, let us say, right driver here. And the bit lines went to the sense amplifier and they also went to the mux. So what should be there in this mux on the bit lines? Do I need a full transmission gate, or can just an NMOS do, or can just a PMOS do? So which of these three should I choose? That is my question.
सर मेरी बिट लाइंस जो है वो सेंस एम्पलीफायर से कनेक्ट होनी चाहिए ना, मक्स और बीच में आपने पैरेलल कनेक्शन दे दिया एक तरीके से.
नहीं, सेंस एम्पलीफायर से तो बिट लाइंस कनेक्ट हो गई.
यस सर. सर फिर वो जो फिर आगे फिर वो सेंस एम्पलीफायर से ही कनेक्ट होनी चाहिए ना मक्स से, आपने पैरेलल क्यों कनेक्ट कर दिया? मतलब
सेंस एम्पलीफायर के आउटपुट पे कुछ मक्स लगेगा, दैट इज अ डिफरेंट मक्स ना. वो तो डिजिटल मक्स है, मैंने कहा आपको. अभी मैं बिट लाइन के ऊपर कह रहा हूँ. See, bit line also needs to be multiplexed to the right driver, ना?
अच्छा, ओके. अभी सर हम वो देख रहे हैं कि राइट ड्राइवर मेरा बिलो है बट मेरा सेंस एम्पलीफायर अबव है. वो कॉन्फ़िगरेशन देख रहे हैं हम, राइट सर?
Yeah.
ओके सर.
So which of the three I should choose? A, B or C?
सर बी. सर बी.
Okay, if this was right driver and this was SA?
Sir, then C maybe.
C.
Then C.
C,
sir.
C. Okay. So do you realize those decisions will also have an impact on how you would design your column decoder?
Yes, sir.
Are you able to see that? So tell me one thing, that let us say another case where there was this mux and both right driver and SA were here. Do you now want to design a transmission gate like this, or you would want to keep the transmission gate like this? So it's not really a transmission gate here. So there are again two configurations possible. Which one would you prefer?
Second one, sir.
Why?
Sir, I mean, in this we are getting the both possibilities, right?
Both
sir,
possibilities.
Actually, I don't see any kind of difference, sir. Actually, I mean, okay, if we can catch the output from the first one
there
also.
Is a clear difference. The difference is that over here, the output of the multiplexer is also shorted. Over here, the outputs, one side goes to, let us say, sense amplifier, the other side goes to right driver.
Okay, so we can keep the right driver circuit and sense amplifier circuit differently. I mean, in first thing they might, I mean, they might.
सर बट सेकंड केस में हमारा दो सेट ऑफ मक्सेस जाएंगे ना फिर एक तरीके से.
क्यों?
सर क्योंकि आप वर्ड लाइन के लिए आप वर्ड राइट ड्राइवर के लिए आप डिफरेंट एक मक्सेस यूज कर रहे हो क्या आप, और सेंस एम्पलीफायर के लिए डिफरेंट सेंस ऑफ मक्सेस.
सेम 2 ट्रांजिस्टर से तो यूज कर रहा हूँ, मैंने क्या चेंज करा?
Sir,
यहाँ भी
if
2 ट्रांजिस्टर थे, यहाँ भी 2 ट्रांजिस्टर थे, क्या चेंज हुआ?
sir, if we can use the second case over here, sir, because the sense amplifier is after the mux, then even small differential voltages can be sensed. So we can use a single NMOS for the sense amplifier, and if the right margin is really good, then we can use this for the word line as well, right driver as well.
So what is the benefit of second configuration over the first configuration?
Lesser area, sir.
Area तो same है. They're same, exactly same 2 devices. There were 2 devices in the first case, there are 2 in the second case also. So what's the benefit of second? If you say you have to go for second, what's the benefit of second?
So can we say that in second read and write can be done at same time?
वो तो एक ही bit line है दीपांक.
Oh, sorry.
Sir, we can keep them both different, sir, actually. I mean, there won't be any kind of interaction. We can keep them both different. So,
okay, so what is the benefit of that?
Sir, in second, writability improves.
Why?
Sir, writing 0 will be easy in second.
The first one may be writing 0 तो easy है, because there is an NMOS through which the right driver का signal will get transmitted to the bit line.
Sir, is it due to the parasitic capacitance? Because here the junction capacitance is in parallel in the first case, and the effective capacitance increases, whereas in the second case it's not that way.
Yes, so it's not just junction capacitance. See, you need to realize that this wire will need to be routed, and then it will be routed inside the sense amplifier also somewhere. And this wire will go to the right driver and will be routed inside the right driver also somewhere. If they were shorted, then all this capacitance would be visible to both right driver and the sense amplifier. When I did not short them, then right driver sees only its part of the capacitance. When it wants to discharge the bit line, only this thing discharges, this thing can be turned off. Do you see that?
सर फर्स्ट में शेड डिफ्यूजन वाला कंसेप्ट नहीं आ सकता, मतलब कि वो भी कम हो जाए, मतलब शेड करके.
Diffusion तो है, but diffusion is a very small component of this capacitance. The parasitic capacitance that gets added due to the other circuit also getting connected is much higher. Shared diffusion वाला तो concept है ही. यहाँ पे अगर जोड़ोगे तो diffusion भी जुड़ेगा. वो तो है ही बात. What I am saying is there is a bigger thing, not just this one transistor का junction capacitance getting added. There's a lot more thing that is coming into picture.
Sir, I think Raghav meant if we use shared diffusion, then the capacitance reduces at that node, if I'm not wrong.
Can you use a shared diffusion between an NMOS and PMOS?
No, sir.
Okay,
Then?
okay.
तो सर मतलब इफेक्टिवली आप ये बोल रहे हैं कि राइट ड्राइवर सेंस एम्पलीफायर को इफेक्टिवली ज्यादा कैपेसिटेंस देगा फर्स्ट केस में, बट सेकंड में हम आइसोलेट कर सकते हैं डिफरेंट सर्किट्स को, मतलब NMOS को PMOS को.
Yes, on the PMOS, the signal that is going on the PMOS, that will include whether it is a read cycle. If it is a read cycle, only then that will turn on, and the NMOS will turn on only when there is a write cycle. So if this particular transistor is not even on, then what happens? Then only the bit line would see only this part of the capacitance.
Yes,
sir. Yes. Bit line sees only this part of the capacitance. If this part is off, the bit line will see only this part of the capacitance. So in both cases, there will be lesser capacitance that you will have to handle. you can be faster. Your power will be reduced a little, not much, but faster you will be. Are you able to see this?
सर सेकंड केस में मार्जिनल एरिया का लॉस होगा क्या हमें, मतलब एज कम्पेयर टू फर्स्ट?
क्यों?
क्योंकि हम सर एक सर हम दो सेपरेट तरह करना चाह रहे हैं तो उतना डेंस नहीं चाहेंगे हम अल्टीमेटली.
See, anyways, there was a wire going towards right driver, there was a wire going towards sense amplifier. Earlier that wire was single wire, now there are two wires. Okay, there could be some additional metal routing required, but only locally in that mux region. Otherwise, there was anyway two independent wires.
Yes, sir.
So you do not yet have that kind of a layout experience. That's why these questions are coming. But you will see that overall you will save on capacitance without any penalty on area actually. Yes.
So, like I got confused. I just want to clarify one thing. When we are talking about the sense amplifier, the signals are coming from upwards, and through the sense amplifier it is going down. And when we are talking about right driver, the signal is going upwards through right driver. Am I right? Okay. Okay. Sir.
Okay. So this is about we are still reinforcing what we discussed in the last lecture. Okay, we are not yet come to today's new concepts. So after that, what did we discuss in the last class?
सर एक्चुअली जब आपने कॉलम डिकोडर 1 कॉलम डिकोडर 2 बता दिया था उसमें ट्री वाला और सिलेक्ट लाइंस वाला, तो सर फिर हम कॉलम डिकोडर 3 में आए थे. उसमें आपने सर बोला था हाइब्रिड है ये सॉर्ट ऑफ. सर वहाँ भी थोड़ा डाइट था कि सर वो फर्स्ट और 2 का हाइब्रिड कैसे था, थर्ड जो 3 वाला था उसमें आपने सर पेज का भी बताया था, बट वो हाइब्रिड वाला कंसेप्ट क्लियर नहीं होता कि वो हाइब्रिड कैसे है, मतलब फर्स्ट 2 का.
उसमें कुछ ट्री भी यूज हो रहा था और कुछ प्री डिकोडिंग भी यूज हो रही थी. That is where we called it hybrid.
सर एक्चुअली वो एविडेंट नहीं था. जो पेज वाला कंसेप्ट था वो मतलब पेज से आप कैसे उसको लिंक कर रहे थे वो थोड़ी एविडेंट नहीं थी सर. मतलब
पेज वाले पे हम बाद में भी आ जाएंगे राघव. पेज पे अभी नहीं जाते. Page we will cover later also. What did we discuss after that? So because we did not discuss page, so that is why I don't want to enter into that yet. We will come to that later. What else did we discuss then after that? Column decoding ke baad.
Different sense amplifiers.
Okay, so what kind of sense amplifiers did we talk about?
सर कन्वेंशनल लैच टाइप सर जहाँ पर PMOS यूज करते हैं. उसके बाद we saw the it with capacitance in between. And after that we had our bit lines running towards the, and like we kept a new NMOS below the latch up circuit, and we give the gate
below the latch up circuit. Latch up?
No sir. So I mean we did the conventional latch type sense amplifier, then we basically shows the working of the sense amplifier key, how the SAF and the SAT nodes work. Basically one goes too little below, then it recharges and it goes just down. And then we basically showed us the that latch basically circuit. I mean 2 NAND gates which were cross coupled.
Okay.
सर थर्ड सेंस एम्पलीफायर में लैच अप सर्किट के नीचे 2 NMOS थे.
लैच अप सर्किट क्या होता है वैष्णव? व्हाट इज अ लैच अप सर्किट?
सॉरी, आई मीन लैच अप सर्किट आई मेंट टू से कि सेंस एम्पलीफायर में जो भी बीच वाला सर्किट होता है ना सर, वो
दैट इज लैच.
हाँ सॉरी,
लैच अप इज अ वेरी स्पेसिफिक टर्म. प्लीज यूज इट वेरी केयरफुली.
यस सर, लैच सर्किट.
दैट इज व्हाट आई वाज फाइंडिंग आउट. लैच अप नहीं है, वो लैच है. Okay, so you are saying that below the latch you add another 2 NMOSes.
Yes sir.
Okay, what happens to those NMOSes?
So those NMOSes are connected to the bit line, and gates are connected to the bit line and bit line bar. So we will be getting it from there. So and like in the capacitor case and in this case, so both the memory unit and sense amplifier can operate at different voltages. That's what the main advantage is in this both. Okay, so we are saying that the capacitively coupled sense amplifier and the third one that we talked about is called alpha type sense amplifier. Okay, in capacitively coupled sense amplifier and alpha type sense amplifier, we could actually have the system operating at the sense amplifier operating at a different voltage than the memory array. So we could really reduce the sense amplifier supply and overall have much significant dynamic power reductions.
Okay, so sense amplifier selling, any questions, any doubts?
सर कैपेसिटिव में था सर कि कैपेसिटिव में एक पॉइंट था कि सॉर्ट ऑफ की क्विज में भी था कि उसमें कि हम जो है सॉर्ट ऑफ सेशन पर होता है कि हम कैपेसिटिव सेंस एम्पलीफायर में थोड़ा एक्सेस टाइम को बेटर कर सकते हैं, रीड टाइम को थोड़ा बेटर कर सकते हैं सर, बट वो चीज एविडेंट नहीं होती है, मतलब क्यों, मतलब सर
Okay, if you
सर
have this capacitively coupled sense amplifier and you precharge it at a Q point, what is the Q point of a device, of a latch, let us say?
Sir, VDD by 2?
Depends on the sizing between NMOS and PMOS, but approximately VDD by 2. This is the place where my latch is maximally sensitive. So what have I done? If I say that there is this, stability thing, that the lower you are, the better it is. So latch could either be at 0 or could be at 1 at different points of time. When I go to the Q point, I have put my latch in this position. So if I see that, oh, there is a slight push towards this side, my output will quickly go to 1. If there was a slight push on that side, my output will quickly go to 0. Otherwise, if both my inputs are at VDD, if both the nodes of the latch are precharged to VDD, then one side will need to make an extra effort to go to 0. The other side is already 1. The first side will need to take an extra effort to go to 0. Are you able to see this?
तो सर जैसे आपने हमें कन्वेंशनल लैच टाइप में बताया था कि एक नोट हल्का सा डिस्चार्ज होगा और दूसरा बहुत फास्ट, तो वैसा ऑपरेशन नहीं होगा यहाँ पे, फिर तब
यहाँ भी
डिफरेंट हो
वही होगा,
जाएगा
यहाँ भी वही
सर, बट
होगा।
यहाँ सर मतलब एक में VDD by 2 में हूँ तो जहाँ पे जो बिटलाइन
अब
डिस्चार्ज
दोनों में
करेगी।
your both the nodes are precharged to VDD by 2 now.
Yes sir.
So let us say there are two balls. There are two balls, both are here. You gave a slight push towards 0 on the yellow ball. Yellow ball quickly came here. And the red ball went there. However, in the other case, in a conventional latch sense amplifier, what was the case? Both the balls were here only. So to take the yellow ball to the other side, you had to first cross VDD by 2 point. And the red ball would have remained here only. So it would take a little longer. Otherwise, both were on the top. जिसको जहां जाना है वो just quickly वहां move कर जाएगी.
So sir, like जो small differential हमें needed था sense amplifier का, उसका और कम हो जाएगा differential basically.
Yes, that is why the sense amplifier will be faster. Now even a small nudge will be able to do the job for you.
Yes sir. Yes sir.
So actually, I cannot say both the balls are here because latch के अंदर दोनों चीजें यहाँ नहीं होती हैं. वो एक अलग स्टेट में ही होगा, दोनों चीजें यहाँ कहीं अलग होंगी. But there is an extra distance to travel. Whereas in this case, both sides follow equal distance and you get a faster output. Okay.
Sort of same principle use होगा जब मैं I'm using MOSFETs for the capacitive coupling, right? When you're connecting direct gate, जब मैं गेट पे कनेक्ट करा था बिट लाइंस को अपने, तो वहाँ पे कैपेसिटिव कपलिंग थी, सेम कंसेप्ट यूज होगा वहाँ भी, जैसा नॉर्मल कैपेसिटेंस भी यूज होगा.
Why? Did we say that it will be a Q point recharge for that particular sense amplifier?
सर बट उसमें भी मैं लाइक अपने गेट से कनेक्ट कर रहा हूँ बिट लाइंस को, तो वहाँ पे कैपेसिटिव कपलिंग ही तो आ रही है हमारी.
Capacitive coupling आ रही है, but this is about Q point recharge. This is not about capacitive coupling. This is about recharging the sense amplifier input nodes that close to Q point.
Okay.
They are two very different things. दोनों को mix मत करो, मतलब confuse मत आओ उनसे. आप कर सकते हो. But the schematic that we discussed, in that there was no Q point capacitive coupling on that alpha type sense amplifier.
मतलब कैपेसिटिव कपलिंग हमें ये बेसिकली सॉर्ट ऑफ एक फीचर देती है कि हम दोनों नोड्स को डिफरेंट वोल्टेज पे ऑपरेट रख सकते हैं, एंड
दोनों
बिकॉज ऑफ
नोड्स
दैट,
मतलब कौन सी दोनों नोड्स?
मतलब जो हमारा जो सेंस एम्पलीफायर के जो इंटरनल नोड्स हैं और जो बिट लाइंस हैं वो डिफरेंट वोल्टेजेस पे हो सकती
दोनों
हैं।
नोड्स नहीं कहेंगे, दो सर्किट्स को। RA would be at a different supply and sense amplifier can be at a different supply.
Okay, so we can put the sense amplifier at different voltages and the VAR at different voltages, and because I'm able to keep the sense amplifier at different voltages, I prefer to keep it at a Q point to make the
I
sense
can.
faster.
No,
Okay,
I prefer
yes,
kaptani. I can. And that
okay,
is what we did. And we saw some benefits. Okay, fine.
okay, sir, okay, sir. Thank you, sir.
So this was almost
Sir,
half the class we spent to review the last class. Yes, please.
sir, I was able to understand the Q point concept, but I was not able to understand that different voltage thing. Like how we are operating our sense amplifier at a lower voltage and our memory array at higher voltage. Like how that capacitor made us do that.
Okay, so let us look at the circuit of the sense amplifier again quickly. This is my SAEN. This is how it is.
Yes, sir.
Okay. Now I say that I want to pre-charge these two nodes to some level.
Yes, sir.
What would this level be? Can this level be independent of bit line supply?
No, sir. We didn't made it independent of bit line supply.
Sorry?
क्योंकि VDD क्योंकि bit lines भी VDD पे है ना.
So because the bit lines are actually connected to the internal nodes of the sense amplifier, therefore this has to be same VDD as the bit line pre-charge ka VDD.
Yes, sir.
There will be bit line pre-charge over here.
So अगर VDD नहीं, अगर हमारे जो internal nodes VDD नहीं होते तो proper translation नहीं हो पाता जो हम देख रहे थे.
ट्रांसलेशन की बात ही नहीं कर रहे अभी हम.
Okay.
चाहे हम अभी हम सेंस एम्पलीफायर को ऑपरेट ही नहीं कर रहे. मैं कह रहा हूँ सेंस एम्पलीफायर इज इन रीसेट मोड.
Okay. Okay, sir.
If it is in reset mode, this supply is pre-charging this. Am I right?
Yes, sir. Yes, sir.
If it is in reset mode, the gates are 0. It
Yes,
means
sir.
they are connected.
Yes, sir.
So this supply cannot be different from this supply.
Yes, sir.
Now let us say instead of this, I used a capacitance over here. Now what happens? Let us say this is VDD low. Will it work?
So अभी connection नहीं है दोनों का, ये दिख रहा है.
So I can operate sense amplifier at a lower VDD, na?
हाँ, अच्छा. Okay, okay, sir.
Because I have removed the physical connection there.
Yes, sir. Yes, sir. Connection नहीं है अभी capacitor की वजह से, that's why we can change VDD, that voltage.
Yes.
Okay.
So
Okay,
the
sir.
coupling has been replaced from a resistive coupling to a capacitive coupling.
Yes, sir. Yes, sir.
That is why.
Okay.
So earlier, when there was a pass gate, when there was a PMOS over there, then it was a resistive coupling. Now it is a capacitive coupling.
Yes, sir. Understood.
Okay.
Thank you.
Yeah. So let's come to today's session then. Anything else from last session? Okay. So let's come to today's session, and we will close with right driver. So there was this question as to what does a right driver include? A right driver can be very simple. A right driver can simply have just a pair of NMOSes which connect the output of this driver onto your bit. So are you able to see this? In fact, this is the mux. This can be the mux signal only. Mux gate only. This can be called column multiplexer, but right driver can be as simple as this. Can such a simple right driver work?
सर मेरा राइट डेटा जो है वो हमारा इनपुट बफर से आ रहा है या फिर इनपुट क्या है वो सर? इनपुट बफर से आ रहा है वो सर?
बफर से आ रहा है। वो तो बफर हमने दिखाया ना, बफर तो अलग चीज है। राइट ड्राइवर बनाने की बात कर रहे हैं अभी। तो सपोज डेटा कुछ आ रहा है, on one bit line you will put data bar and the other bit line you will put data, and that should work. Is it fine?
सर आई मीन मुझे दूसरे उसकी जरूरत क्यों है इन्वर्टर की?
Okay, you have a bit line pair ना?
नहीं सर, मतलब मुझे बिट लाइन बार बिट लाइन चाहिए, बट मैं आई कैन वर्क विद ओनली वन इन्वर्टर ना, बिकॉज आई एम काइंड ऑफ बफरिंग द राइट डेटा देन टू कनेक्टिंग टू द अदर बिट लाइन. व्हाई आई एम डूइंग दैट?
Okay, so suppose let us say आपने एक इन्वर्टर लगाया, तो दूसरी बिट लाइन को आप ड्राइव नहीं करोगे?
So that can be directly connected with the right data, right?
Oh, so can we allow the memory inputs to directly go inside the bit and see the bit line capacitance? We discussed that already. Do we want to do that?
No, sir.
No, sir.
सर बिट लाइन कैपेसिटेंस दिखेगा ना, उसको तो हमारा मक्स का दिखेगा ना, ये राइट वाले N2 का दिखेगा, मतलब राइट डेटा को तो.
राइट, जब राइट 1 होगा तो पूरी बिट लाइन की कैपेसिटेंस दिखेगी ना?
यस सर.
Is it okay?
No, sir.
है ना? So anyway, आपको इनपुट को तो बफर करना पड़ेगा, and you can only use buffered inputs inside the memory. My question is something else. Is this sufficient? Is this right driver sufficient, or do you want to do something else to it?
Sir, during write operation, we need BLT and bitline and bitline bar to 0 and 1. So as I can see, there is only one latch which is operating and it's maintaining the same voltage towards both. So
Sorry?
actually this is doubt.
नहीं, दोबारा से. What did you see there?
Sir, बीच में
Bar
एक
and
latch.
bit and minus bit. Okay, bit and minus bit over here will actually be driven to opposite values, no?
Oh shit! Sorry. Yeah. Yes, sir. Yes, sir. Sorry.
Sir, should we include a transmission gate to write a complete 1 and 0 on both bitline and bitline bar?
Good. We may want to, Ranjit. We may not want to. So if I do not keep a full transmission gate, then what do I need to do? I need to put another PMOS over here, which is controlled by the other bit line. You think that would work?
Yes, sir.
So there are multiple ways to handle this. So that this circuit was incomplete in itself. You are absolutely right. We needed some semblance of a transmission gate, or we needed a PMOS, cross-coupled PMOS like this. Okay. In addition to this, we already talked about write assist schemes. So when you design the right driver, you also need to take care of designing circuits so that your bit line can be taken to a negative bit line level, so that you can have negative bit line write assist scheme. So there are some capacitors in advanced right drivers. You will see that there are some capacitors that are also put there. There is some tracking circuitry that you may want to put there, so that whichever side you want to write a 0, on that side, after 0 has been written, the capacitance is triggered to generate a negative bit line. Okay, so this is a very simplistic view of a right driver, and for top level understanding, that is fine. But when you will enter into your projects and you will be making your right drivers and stuff like that, then you have to take care of being able to generate negative bit line also. Okay. Additionally, there is another feature called mask, or let us say bit write. What this means is that in a full memory, there could be, say, 72 bits. Suppose this memory is being used as a L1 cache, and there is a 73rd bit which is called dirty bit. If my cache coherency requires that some other processor has written data into the same location in another cache, then I would say my caches are no longer coherent, and I would put dirty bit. I would want to make dirty bit equal to 1 over here. I only want to write on one bit and not on the other bits. This kind of a feature is called as bit write. Why do I write? What is the benefit of this kind of a feature? What do I save or what do I gain?
Power.
Power. And in the example that we just considered, probably one cycle of the CPU also, because now you'd say I do not need to get the required data from the other core which had made the coherent cache, made the change in the coherent cache. I do not need that data. I will simply put the dirty bit equal to 1. I will transfer that data only when this particular processor also requires the same information. Otherwise, I will just put a dirty bit. So you also probably save a few cycles of the processor. Maybe not always, but at many times. Is that okay? Are you able to see this?
सर ये एक्चुअली डर्टी बिट हमें क्यों चाहिए सर? ये बिट रेट वाला थोड़ा सर
So you've not done the course
confusing.
on computer architecture? How many of you have done the course on computer architecture? You can put a +1 in the chat window. Okay, so quite a few have not done. So in a multiprocessor architecture, there could be a memory or a memory system which are so three memories which are shared across two cores. Okay, two processors wanting to access same data in two different memories. Let me go to whiteboard and try to explain it there. So let us say I have processor 1, I have processor 2, and they are supposed to operate in sync with each other. Okay, they have different instructions, they have different stuff coming into it, but they are supposed to be in sync with each other. What that also means is that the content of the memory may also require to be same. Now, it so happens that this processor updated a particular address location over here. Now, because they are to be in sync, you can actually just tell this processor that, bhai, there is a dirty bit here, put that dirty bit 1, and you do not need to write this new information over here at the same time. Why? Because most probably this particular address is required only in this core. There is a set of instructions that are operating only on this part of the data. This particular core could be working on, let us say, another part of the address of the contents there, not the ones that this core was working on. So because this core will never access or will not usually need to access this part of the data, let me just write a dirty bit. Transmitting a dirty bit is much lower power for the bus, is also faster for the bus, and also over here I save dynamic power because I'm just writing one bit, not all the bits of the word. So I save overall power, and I also save transmission of all this data, and therefore probably one cycle also.
सर मतलब जो हमारा कोर 1 है वो जो मेमोरी में जो भी अपडेट कर रहा है या फिर जो भी ऑपरेशंस कर रहा है उसका बेसिकली काइंड ऑफ एक उसका बेसिकली काइंड ऑफ हिस्ट्री हमारे पास कोर 2 के पास होनी चाहिए बेसिकली.
Yeah, because they are supposed to be synchronized cores.
और सर वही जो हमें जो कोर 1 के मतलब ऑपरेशंस को कोर 2 ट्रैक करने के लिए जो इस्तेमाल करेगा उसको हम डर्टी बिट बोल रहे हैं बेसिकली, जो
या
ट्रैक
लेट
करने
अस,
के लिए
चलो इससे थोड़ा सा आसान एग्जांपल देख लेते हैं। यहाँ वाला तो थोड़ा सा मुश्किल हो रहा होगा, आसान एग्जांपल देखते हैं। लेट अस से देयर इज एन L2 cache which is definitely shared across 2 cores. Okay, now this particular core updated one particular address. This particular core also had the same address called over there, but it was long back, long back. Okay, so what happens is, as soon as L2 cache is updated, you know that this same L2 cache location was put in L1 cache also. So you only update the dirty bit here. You do not bring the new data from L2 cache and then write it all together into this core.
Okay.
Is this clearer?
So जो dirty bit है वो हमारे L1 कैश में हो रही है, मतलब अपडेट।
Yes. L1 cache में अपडेट हो रही है।
और सर इस आर्किटेक्चर के हिसाब से L1 कैश जो है कोर 1 कोर 2 की डिफरेंट है।
यस, वो तो पहले भी मैं बता रहा था डिफरेंट ही थी, बट मैं L2 कैश दिखा के सिंक्रोनाइजेशन नहीं दिखा पा रहा था आपको, मैंने वो भी ऐड कर दिया। आई जस्ट एडेड द कंप्लीट व्यू देयर फॉर यू।
ओके, सो सर L1 कैश कोर 2 ने पहले एक्सेस किया था L2 को, बट इसने कुछ अपडेट किया तो इसने इस अपडेट को L1 कैश ऑफ कोर 2 में थोड़ा सा डर्टी बिट के थ्रू उसको बेसिकली इन्फॉर्म कर दे कि वहां पे कुछ अपडेट हुआ है।
Yes. Okay. So for this kind of a operation, you need what is called as bit write. Okay.
So this operation whole is called as bit write.
No, being able to write only into one bit and not the entire word, that is called bit write. Or selective bits and not the entire word, that is called bit write. We also call it mask, that the remaining 64 bits are masked, only one bit I am writing into. Or remaining 72 bits are masked, only one bit I am writing into.
So one bit of L1 cache only I am writing into.
Yeah. Okay. So it saves dynamic power and it also saves lots of processor cycles many times. Okay. So write driver is not really as simple as it appears to be here. Those of you, when you will pick up the projects, you should implement mask and also negative bit line in your write drivers. Okay.
सर एक और चीज थी सर, अगर मान लीजिए मुझे L1 कैश को मतलब वो अपडेटेड डेटा चाहिए होगा, देन इट विल यूज दिस बिट डर्टी बिट इंफॉर्मेशन टू देन फेच द डेटा, मतलब जब चाहिए हो तब वो ले ले। ओके।
Yes.
ओके सर, थैंक यू सर।
So now let's have a quick refresh of how different memory operations happen. Do you remember this graphic from earlier? We said there is a word line selection that is going to happen like this, and there is data that will come like this, and there will be some signals that will be flowing like this. You remember all this?
Yes, sir.
So now tell me, before the word line gets selected, which signal over here should have reached the particular IO? Suppose we're talking about the last IO over here. Which signal should have arrived in the IO before the word line arrives in the array? Are there any such signals?
सर राइट वाला जो राइट सिग्नल था सर।
You say right clock should arrive before the word line arrives. Because what we said was that before the word line arrives, my bitline and bitline bar should have been taken to 0 and 1 levels, wherever whatever was the appropriate requirement. That is what we want. Huh?
Yes, sir.
Friends, why is it that only one or two people are speaking? I'm talking to the entire class. Please, I would be happy to have more participation. So what we are essentially saying is that when we talk of all these operations, read and write operations in the memory, there are signals that are racing against each other. Over here, there is a race between word line and, let us say, bit line reaching 0 and 1 level before the word line arrives. Or let us say in the read cycle, there would be a race between before word line arrives, the pre-chart should turn off. That kind of a race would be there. Hello?
Yes, sir.
So now that we are looking at circuits on the periphery side, we also need to be aware of the fact that there will be race conditions like precharge should go off before word line is selected, or that right driver should switch on much before word line is selected. Why much before? Because it has to discharge the bit line also. Or that sense amplifier should be enabled only after the worst bit cell also has discharged sufficiently well. So there are these race conditions that exist inside the memory. If these race conditions are violated, there could be loss of yield, there could be loss of power, there could be loss of performance. All three things. Okay. So as a memory designer, you would need to necessarily do what is called as race analysis or marginality analysis. Why marginality? What is the margin? How early does precharge go off before word line arrives? That's the kind of margin. So we want to see what kind of margins exist inside the memory so that memory doesn't fail. Okay. And all these margins, whenever we talk about verification, see, whenever you talk about characterization, you would do at SS, say SS 1.08 volts, 125C. But whenever you talk about these margins, then you also need to check at SS 1.32 and 125. Okay, you also need to check at SF and SS lots also. So when you talk of checking these margins, you do not want your memory to fail in any case. So all the different cross corners are also tested and verified to be fine when you do marginality analysis. Okay.
So margin of timing difference को ही बोल रहे हैं जो time
timing margins है.
और सर रेस क्या है सर? सर रेस एनालिसिस क्या है फिर?
Same.
अच्छा.
Just that रेस को रेस के बाद आप जो मेजर करते हो मार्जिन मेजर करते हो, है ना? That is what's called margin analysis, marginality analysis. But someone may also call it race analysis. Which signal came faster? But which signal came faster is insufficient information. I actually need to see what are the margins there. That is why I prefer to call it marginality analysis. Okay.
So I have one thing to ask, like for any analysis एक वर्स कंडीशन होती है पीवीटी की, तो हम 4 पे मतलब 4 पे या ज्यादा पे क्यों चेक करें? वर्स हम अगर हमें वर्स पता है तो वर्स पे चेक करें बस.
So क्या आपको ये पता है कि रीड के लिए जो वर्स्ट है वही राइट के लिए वर्स्ट होगा?
नहीं. अच्छा.
ये तो मैंने अभी आपको 3 कंडीशंस यहाँ पे लिख के दिए हैं. जब आप रियल में मेमोरी एनालिसिस करेंगे तो यू विल नोटिस दैट देयर आर more than 30 conditions.
Okay.
Yes, you can actually see, you can actually write 30 different test vectors, 30 different this, and then run only on one PVT each. You can do that.
Yes, sir.
No problems.
Okay.
I prefer to say, okay, there's no harm in measuring what is the margin even on a PVT where it is not critical. I would rather measure everything, but reduce my work.
Yeah, yes, sir.
सर इसमें सर थर्ड वाले पॉइंट में एक डाउट है. सेंस इनेबल जो है उससे हमारा यील्ड पे कैसे इफेक्ट हेलो
या
सर जो सेंस इनेबल वाला,
अगर सेंस इनेबल जल्दी आ जाएगा तो क्या होगा?
सर फंक्शनैलिटी may get affected because I may not able to ensure कि correct read is happening, but yield तो सर हमारे लिए प्रोसेस का पैरामीटर होता है ना कि.
But memory तो self timed है ना राघव? If you reduce the memory clock, do you think you will be able to recover this cell now?
Sir, clock reduce मतलब sir?
See, when you would call it a functionality issue and not an yield issue.
सर्किट है वो हमारा सही है, बट हमारा बेसिक ऑपरेशन गलत हो गया, बट यील्ड मतलब हमारा सर्किट ही कुछ प्रॉब्लम है उसमें.
So there is an AND gate something somewhere which works fine, but when it is in the system, because of some timing failure, it doesn't work fine. Something like that is what you're referring to?
Yes sir,
तो
मतलब सर
circuit is fine, but timing का issue है.
मतलब हाँ सर, एक दो ऑपरेशन उसने गलत आउटपुट दे दिया, फिर ऐसा कुछ हो गया तो उसमें फंक्शनलिटी.
उसमें कोई issue नहीं है. That's okay. You wanted to apply brakes and it accelerated the car. Fine with you. You will sit in that car.
No sir. No.
No. So it's a failure.
Yes sir.
Now for the NAND gate, you could probably slow the clock and say instead of latching NAND gate after 20 picoseconds, I will latch it after 30 picoseconds. And you could recover yield.
Yes,
in the
sir.
memory, you
Yes.
can't do that. In the memory, the sense amplifier enable is not controlled by you. It is controlled by the memory itself. You slow down the clock as much, the enable will still come at the same time. So this is a permanent yield loss.
Okay. सर एक्चुअली मैं इससे रिलेट कर पा रहा हूँ. सेंस इनेबल आपने बताया था कि इट इज समहाउ रिलेटेड टू काइंड ऑफ वर्स सेल, और उसमें आप एक एक्स्ट्रा जो बिट बीएल करके आपने एक एक्स्ट्रा बीएल बता रखी थी वर्स केस के लिए, कुछ रेप्लिका करके. तो सर उस अगर वो खराब है तो इसका मतलब हमारा वो वाला पाथ पूरा खराब है, मतलब इसलिए हम यील्ड लॉस सॉर्ट ऑफ ऐसा कुछ है.
सेंस एनेबल
Okay.
वहीं से आ रहा है ना. यहाँ पे हमने वही बात तो करी है. We have said exactly the same thing over here again, no? We're talking about the verse cell only.
ओके, सो मतलब हमारे ओके, तो हमारा वो जो पूरा सर्किटरी है वही कहीं डिफेक्टिव है, इसलिए हमारा ओके. यस सर.
No, it is operating faster than it should be. So it's a failure.
यस सर, उसको आप रिकवर नहीं कर पाएंगे.
That's an yield loss.
Yes,
Okay.
sir.
So now let's come to decoder design. Now it might appear to be simple. Oh, you just need to make a 9 to 512 output decoder. But it is not as simple actually. How you design a row decoder, how you design the decoding circuits has a very strong impact on how the memory is organized. So for example, it would define how the words are scrambled inside the memory. So what is scrambling? Did we discuss that already?
Sir, bit interleaving if I'm not.
Huh?
Bit interleaving?
Yeah, bit interleaving. So that is one aspect of it. Let us say there is this memory. I could start to write word 0 here, or I could write to start word 0 from here. Is it right? I could have row 0 selecting the topmost row, or it could be selecting the bottommost row. That is a choice as a designer I have, na?
Yes, sir.
Or I could actually write row 0 somewhere here and then go this way and then go that way. I can do whatever I wish to do as a designer. Are you able to see this?
Yes, sir.
So this is what we call as scrambling. Memory bit scrambling, where are different words and bits corresponding to different addresses. So when a particular address is asked for, which row gets selected? Does this row get selected, or this row get selected, or which column gets selected, this one or this one? Why do you think this information is important?
Sir, for correct read and write operation. I mean,
जो भी आपने एड्रेस दिया वही हर बार सिलेक्ट होगा, तो करेक्ट रीड राइट तो हो ही जाएगा. ये थोड़ा ना होगा एक साइकिल में एक एड्रेस गया, दूसरी एक रो सिलेक्ट हुई, दूसरी साइकिल में सेम एड्रेस पे दूसरी रो सिलेक्ट हो गई. दैट लॉजिक यू कैन नॉट चेंज. इट इज हार्ड कोडेड. यू हैव NAND gates, you have everything hard coded inside your memory. So why is this information important?
सर apparently it seems कि अगर हम हमारा शायद से जो हमारा IO सर्किटरी है मक्स है उसका डिजाइन में शायद से चेंजेस आ जाएंगे मे बी.
वो तो मैंने चेंज करके इसको कर दिया चेंज. दैट इज फाइन. But why is it important? Why do, as a designer, you need to know it? Why would a SOC designer also need to know it, if at all?
sir, for testing to see if it's working fine or not. I mean,
So testing में तो you can simply read and write into one location and see if it was what you had written is what you read. That is good enough.
Sir, when we select, a doubt, sir, over here. So when we select, how do we see if one particular memory cell is being is being selected or not with the help of I'm like this select lines only, right? I'm sorry, the row selector, right? Row selector and the column selector, right? So अगर वो ठीक तरह से काम कर रहा है कि नहीं वो check करने के लिए I was saying that actually I'm like it's
So look at
needed.
it like this. I said that, okay, I said that this should be row 0. I said that, okay. However, I ended up designing this to be row 0. Will it change for the user anything? No, user sent an address for row 0. In one case, this row would have been written into and read, or in another case, this row would have been written into and read. Whatever I wrote, that is what I am reading. For the user, it is not changing anything. How will the user make out whether the bottommost row has been selected or the topmost row has been selected? Can the user make out?
No, sir. I was speaking from the designer perspective actually. So designer
Even as a designer, you put something on silicon, you wrote and you read. Can you make out where the row was?
No.
So for all practical purposes, do you need to know the scrambling? And the practical purposes that you are telling about, do you need to know that scrambling?
No need, sir, actually.
But then I'm still talking about scrambling, and I'm saying that this is important to understand. Why?
So maybe when we program or defining memory map for peripherals for an SoC, we need this information to optimize the top system level program, maybe.
Okay. Other ideas?
Sir, maybe if this memory mapping is present with us, then we can choose the rows where the data has to be written apart, which are frequently used, so that the crosstalk can reduce something of this kind.
Yeah. So thank you, Ranjit. Let me say that I read the entire memory and 2 particular addresses failed. Now, if I do not know the scrambling, I would not know that these 2 addresses that are failing are actually right next to each other. Those rows are placed right next to each other, and they are failing because there was crosstalk between them. So I need the scrambling information to debug. That is one aspect. Then some of you also mentioned, if I know the scrambling information, I can somehow design better, in the sense that I can say that there is this my entire memory there, okay, and that memory is split into, let us say, banks. So I would say that I would want to distribute my reads across banks so that none of the banks is overly stressed. So I would deter and I would write my data into different banks, even though they are consecutive data. So this is word 0 in one bank, word 1 in the other, word 2 in third, and word 4 in the topmost bank, or word 3 in the topmost bank. So I know that, okay, I may write consecutive words, but in the memory, let them be spread far apart. Why? Simply because when I will read them again, I will be reading them one after the other. Then let me not stress any one bank too much. None of the banks should be stressed too much. I need 4 consecutive words, so I will actually access all the 4 banks, and it should be fine. I would not degrade any bank. I would not cause aging, too much aging on any bank. I would not cause too much stress on any bank. So I'm not saying you should do this. What I'm saying is, if you know the scrambling, you can start to think on these lines.
Sir?
Yes.
सर स्क्रैम्बलिंग से आप यही बोल रहे हैं कि अगर मैं कन्वेंशनल डिजाइन देखूं तो मैं वर्ड 1 वर्ड 2 वर्ड 3 वर्ड 4 एक सॉर्ट ऑफ एक लॉजिकल कंसेक्यूटिव ऑर्डर में कर रहा हूं, बट उसकी ना करे हुए मैं कहीं भी वर्ड 1 वर्ड 0 कहीं भी प्लेस कर सकता हूं, मतलब अलोंग द रो। ऐसा नहीं कि वो कंसेक्यूटिव होना चाहिए। इसको मैं स्क्रैम्बलिंग बोल रहा हूं, राइट सर?
Yeah, let us simply say Abhi, if I want to say word 0, word 1, word 2, word 3, right next to each other in a given row, huh? Which address bits will you send to the column mux? Which address bits will you send to the column mux for decoding this? 0, 1, 2, 3. I want to
Sir, जो
decode
LSB, sir, LSB शायद से.
LSBs, address 0 and address 1. Huh? Now let me say that instead of word, so this is word 0, this is word 16, this is word 32, this is word 48. Okay. Now which bits am I sending here?
सर यहाँ पे आप LSB सेंड करोगे, मतलब कॉलम में MSB जाएगा.
MSB जाएगा.
तो यहाँ पे LSB जाएगा, यहाँ पे LSB.
LSB रहेगा A0 and A1.
No sir, MSB रहेगा.
MSB रहेगा. What is the
नहीं,
MSB?
Sir, to select this row, we need to
Row
select.
की बात नहीं कर रहा. I'm asking what happens in the column mux. Which what addresses should go to the column mux?
Sir, MSB.
Sir, MSB, sir.
MSB. Why do you say MSB? My MSB would be related to my, like I have a 1K word instance. So I have 10 address bits. MSB डालूंगा तो how will I select amongst these?
सर मेरे वर्ड 0 वर्ड 16 ये एक रो में है और मैं इस रो में जब सिलेक्ट करूंगा तो मेरे साथ सारे सिलेक्ट होने चाहिए, राइट? मतलब वर्ड 0 वर्ड 16 वर्ड 32 वर्ड 48 ऐसा चाहता हूं सर मैं कॉन्फ़िगरेशन.
वर्ड लाइन तो सबको एक साथ ही सिलेक्ट करेगी ना राघव?
यस सर.
I want to choose one of these words now. What should go into this multiplexer? Which address bit is changing in between them, amongst them? Is anything changing amongst the bottom 4?
No sir.
Where is the change happening?
Sir, in between.
So this is 16. So this was initial was 0. Hai na? This is 16. This is 32. This is 48. Are you able to see this? So which bits would go there?
Sir, we can use MSB.
MSB.
Again, this was a 10-bit address.
Oh, yeah.
Can you use MSB?
No, sir.
No, sir.
What bits are we talking about?
Sir.
Intermediate, sir. I mean,
5 and 6.
A5 and A4.
Okay.
Yeah.
So which bits you send to the column multiplexer will decide which words sit next to each other in a row. Do you see this?
So, but why will I want to do that? Making so complex it. I mean, I can go
What is
with word
complex
1.
in this? What is complex in this?
So, I mean, my question is, why would I prefer this over, say, word 0, word
I'm
1,
not
word
saying
2?
why would I prefer this. I'm saying
Okay.
how you manage the address bus can impact memory scrambling. That how you manage the address
So, like,
would impact memory scrambling. Are you able to see this?
okay. So, sir, how I'm placing the different words in the array, that is kind of the scrambling. And that will be impacted by how I choose to, which bits I choose to select in the row and the column.
So the same memory, Raghav, in the same memory, if I just change which pins come to the column mux decoder, the words in that the memory scrambling would change. Nothing else has changed, just which inputs I am connecting to the address decoder on the column side, that will change the memory. Are you able to see this?
Yes, sir, the memory organization will change depending on which bits I'm sending.
Sir, this example seems to be too suitable, sir. So if we take word number 47 over there, then it will be different, right?
Word number 47 is in some other place, yes. It is in some
Okay,
other
so
row.
Scrambling, I'm like we do the scrambling based on this two select lines. I mean, we first maintain any two select lines constant and we'll vary those conditions of 4, and according to that we make scrambling. Is that what you meant? Or I mean,
what I mean is how you connect your address bus to different parts of your circuit will change the memory scrambling entirely.
हाँ sir, वो ठीक है.
That's it. Now, depending on what your purpose is, what your processor needs, what your system needs, you can use your address bus appropriately.
सर इसमें बैंक कहाँ पे था फिर? बैंक क्या चीज थी सर?
मैंने बैंक की बात नहीं करी अभी, मैं तो खाली अभी एक रो के अंदर आपको दिखा रहा हूँ, बिकॉज रो वाली चीज आपको ऑलरेडी क्लियर थी, है ना? रो थिंग वाज ऑलरेडी क्लियर टू यू, सो आई एम जस्ट इलैबोरेटिंग ऑन इट. नाउ लेट्स कम टू बैंक. बैंक वाला मैंने शुरू करी थी बात. या प्लीज. यस.
So sir, ये जो memory scrambling कर रहे हैं, this will be done based upon the my processor needs. What exactly?
You can.
Okay.
Or you may not. That's okay.
Okay.
If you want to optimize something, if you are a memory, if you have done this course to now, tomorrow when you go to wherever you go to, as an architect, you know, okay, this is possible and that is not possible. Someone who has not done the memory design course would not be able to handle it like this. Are you able to see this? Now let us say these are my banks. Suppose I want to put word 0 here, word 1 here, word 2 here, word 3 here. Which address bits do I need to use for bank selection?
A0, A1 sir.
A0, A1. Huh? Now, if I say that, okay, word 0, word 16, word 32, word 48. Now, which addresses?
A5, A4.
A5, A4. So, again, which address bits you use for bank selection will again define how your words are distributed inside the memory. Huh? Are you able to see this?
So, but if bank चीज है क्या sir? I mean,
bank is if okay, bank means let us say you have put extra IOs somewhere. This is hierarchical bitline architecture. We'll come to that a little later, but okay, chalo, let me take it now because it is a part of address decoding only. So let us say I had a memory which had this bigger bit line, this longer bit line, due to which its speed was 2 nanoseconds. Okay? I want to operate at 1 nanoseconds. So what I do is I say, oh, this bitline capacitance is huge. Let me separate or split these bitlines into smaller bitlines. Each of these smaller bitlines will be associated with a sense amplifier. And there will be a global line through which I will be able to give an output. What happens? Now, because the bitline capacitance that every bit cell sees is smaller, this access time would come down to 1 nanoseconds. Because you have reduced the overall capacitance. So this is called hierarchical bitline.
Sir, is this same as the page that we discussed yesterday?
Yeah, that is another way of saying that, okay, अभी मैंने आपको vertically place करके दिखा दिया. There could be multiple such arrays which I could place next to each other. And again, one of the address bits would select one of the pages. One of the address bits would select one of the banks. Is this okay?
Sir, I mean, a general question, sir. So, ये scramble जब हम लोग कर रहे हैं ना सर इसमें, so previously during bit interleaving you explained that okay wiring का issue है, so we have scrambled that. इसमें issue क्या हो रहा है कि हम लोग scramble कर रहे हैं at the first place? हाँ, that was my question, sir. What's the issue that we are scrambling actually? I mean, why do we want to?
Suppose you were not using mux. Let us say you were not using mux. 1K words, 8 bits. What would be the die aspect ratio of your memory? Why did we talk about scrambling in the first place? Do you remember?
Yes sir, I mean different positioning different होगा, इसीलिए we were seeing scrambling. But okay, before that why do we want to actually scramble that? So okay, एक चीज था जो bit interleaving था, वो समझ में आ गया. But okay, ये जो भी है word
Scrambling का
0.
मतलब क्या है? Scrambling का मतलब है how are the words placed? That's it. You have to place the word somewhere, na? If you do not want to give any scrambling information, you have to place them linearly. The moment you say I will fold the memory and use mux, you need to tell where is which word. Are you able to see this?
Yes sir.
As soon as you start to use mux, you have to tell na where is which word, which row, which column.
Yes.
That's it. That is what we are calling about. That is where the scrambling thing comes into picture in the first place. Now, you not only use mux, you also use hierarchical bit line. So now you need to know which bank is which word. It is not simple. So as you add more complexity to the array, for whatever reasons, you need to tell the user where is what. Because depending on where what is, let us say a set of 20 words are failing, 24 words are failing. They are not consecutive words. Unless you know the scrambling, you will not be able to make out that, oh, this particular sense amplifier is actually what is failing. You will say, oh, 24 random failures are happening. I do not know why. But as soon as you know the scrambling, you will realize, oh, they're all linked to one same sense amplifier. So it is not that the bit cells are failing, it is that the sense amplifier is failing.
Yes sir. Yeah.
Are you able to see this? That is why as a designer, you should know how the words are distributed so that if there is any failure, you can quickly tell, oh, this is the common circuit. Oh, that is the common circuit. Okay.
सर इस केस में जो हमारा बैंक है, इस केस में जो पूरा कॉलम है, कॉलम को हम मल्टीपल एक शेड बिटलाइन की बजाय हम एक मल्टीपल बिटलाइंस को हमने तोड़ दिया, मतलब different parts.
This is called hierarchical bit line.
Okay. And
We
sir,
made the
each
bit line capacitance smaller.
Okay. So sir, like each basically kind of bank will correspond to a certain set of bits of a certain set of words basically.
Yeah.
एक बैंक में कुछ words आएंगे और उनकी कुछ bits होंगी.
Yeah. Okay. So I would say, think about these questions. What if LSBs are used for page selection? How would the scrambling change? What if MSBs are used for page selection? How would the scrambling change? Similarly, we just did that. अभी हमने अभी यही कर लिया. I would say just stay with this thought and do more of this before the next class. A little bit of it before the next class. Okay. Then we will look into address decoding in much more detail in the next class.
सर एक डाउट था इसी में बैंक वाले में. सर फॉर एग्जांपल जो मेरा एक सॉर्ट ऑफ सेट ऑफ बिटलाइन होगा, उसमें हमारे कॉलम्स होंगे. मान लीजिए 5 रोज हमारी एक बिटलाइन कवर कर रही है, तो उसकी कुछ बिट्स होंगी. फॉर एग्जांपल बिट 0 है हमारी, तो अगर मान लीजिए मेरा वो बिट्स फेल कर रही हैं, मान लीजिए वो वर्ड 1 वर्ड जो हमने करा था वर्ड 0 वर्ड 16 48 32, वो हमारी एक की लाइक कॉलम में उनकी बिट 0 थी, ऐसी आ रही थी. तो अगर मान लीजिए इन चारों की अगर बिट 0 मतलब फेल हो रही है, या फिर इनकी वर्ड में रीड कर रहा हूँ तो इनकी बिट 0 फेल हो रही है, तो फिर मुझे ये अगर मुझे क्या कहते हैं बैंक वाली इन्फॉर्मेशन पता होगी तो मैं ये वहाँ पे लोकेट कर पाऊंगा कि वहाँ पे सेंस एम्पलीफायर खराब था, ना कि उन 4 वर्ड्स की बिट्स खराब थी. ये बोलना चाह रहे सर आप?
Yes.
Okay.
You will be able to localize faults and errors very quickly.
Okay.
Okay. Chaliye. Good guys. Thank you. All the best. And I will stop the recording now, and we will meet again. Oh, okay. So tomorrow I have office hours. We can meet there. Otherwise, we will definitely meet on Thursday. Okay. All the best, guys. See you.
Thank you, sir.